This is the workbook homework helper for Chapter 2, Section 6, entitled Prime Factorization. So up top in 1 through 8, what they're asking you to do is to tell whether the number is to prime or composite. Remember, what prime means that the only numbers that make the given number, in terms of positive integers, are one in itself. If there's another set of numbers that I can multiply together to make that number, it's composite. If not, it's prime. So if we take a look at question number 1, 33, we know that 33 is 1 times 33. No question. 1 is always going to work with itself. But is there something else? As long as there's something else, this is easy. Right? And in this case, we know 3 is going to work because 3 times 11 is 33. And that's what makes this a composite number. If there's others, great. There doesn't have to be, though. As long as there's just one other, right, that's what makes it composite. Now with 41, you've got 1 and 41, but what else? Well, there's nothing else. You can go through the list. You know the even numbers aren't going to go in because itself is not an even number. 3 isn't going to work. 7 isn't going to get in there. 13 isn't going to get in there. 17 isn't going to get in there. There's none of those other numbers that are going to fit into 41. And so that makes it a prime number, in that the only way to make 41 in terms of the positive integers is 1 and 41. Now what they have you doing in 9 through 32 is they have you writing the prime factorization. In other words, creating factor trees, because factor trees are how we generate prime factorization. So let's go ahead and take a look at those questions. Right? And we'll take a look at question number 9 and question number 10, and you can apply what you see there to the other questions. So in number 9, the number we're working with is 57. Remember, when you're making a factor tree, a branching diagram in essence, you're looking for numbers that multiply together to make the number above it, and you get to stop when you get a prime number on a branch. And your goal is to have all the branches end up at prime numbers. So with 57, we should see real quickly here 3 and 19. 19 times 3 does make 57. And that's a good choice because 3 is a prime number. The only way to make 3 is 1 times 3. And 19 is a prime number. So that means we're done. We've primed out all the branches of the factor tree. We could keep going if we need to and make more branches, but we don't need to because we've all prime numbers. So on the blank where they're asking you to write the prime factorization, you're going to write 3 times 19. Now we'll contrast that with number 10, 49. And 49, again, not a lot of options here. You're going to have 7, 7 and 7, which doesn't look any different than the last question. Both are prime numbers. The only way to make 7 is 1 times 7. But what's going to look a little bit different is how I write my answer. I can write 7 times 7, but you can also write prime factorization with exponents. So what the book would write here, what they want you to write, is not 7 times 7. They want you to write 7 squared. And as we know from studying exponents, 7 squared is actually the same as 7 times 7. Same idea, just different way to write your answers. Okay, let's take a look at one more question because really we have not had a question yet that's branched below one level. So let's get a question where we actually have to go down through more branches here with 88 in question number 11. 88 is going to branch out as 8 and 11. Now the 11 branch is not any different from the previous questions. That side's done. It's a prime number. The only way to make 11 is 1 times 11. But 8 can break down. 8 is not a prime number. Right? There are more ways to make 8, like 4 and 2. And 2 is prime, but notice, hey, 4 isn't. 4 can still be broken down. So we're going to have to go yet another level down way bigger than the previous tree diagrams, and that's going to be 2 and 2. And those are prime numbers, and now that I've primed out all the branches, I can write my prime factorization, which is 2 times 2 times 2 times 11. Right? Or if we want to write this with some exponents, because we can see 2 shows up 3 times, 2 to the third times 11. And of course, you can check any one of these. If we go back up here to this one, 7 times 7 does make 49. So as far as that part goes, as long as we have all prime numbers, that's good. 2 times 2 times 2 times 11. 2 times 2 is 4, times 2 is 8, times 11 is 88. So that's how we know we did this one correctly, as long as we have all prime numbers in our answer. One thing to point out, though, as I'm saying all prime numbers in the answer, the exponent does not have to be prime. The bases, if you write them as powers, will be, but the exponent does not have to be prime. But these big numbers, like the 2 and the 11, again, those would be the bases. This would be like 11 to the first if you want me to get hyper technical, right? Those do have to be prime numbers, though.